Okay, next topic that we're going to talk about for today is linear and volume expansion. So, according to the linear and volume expansion, it says here that when the temperature of an object is changed, okay, by amount delta T, it would result to a change in its, length, okay? And that change in length is given by the following formula. We have the change in length is equal to alpha times the initial length of the object, L sub I, multiplied by the change in temperature. So let me write that down. Just we have there where delta L stands for change in length, alpha alpha is the coefficient of linear expansion, L stands for L sub I stands for the initial length or the original length of your object, and delta T stands for the change in temperature. Okay, so the change in length naturally is in meters, the initial length is in meters also, and the change in temperature is expressed in kelvins or sometimes Celsius degree. So the coefficient of linear expansion, to get the desired unit, which is unit for length, is just simply 1 over k, or some people just write it as k to the negative 1. Okay, so that's it. That's for the coefficient of linear expansion. But when we talk about volume expansion, on the other hand, we just follow the same formula. By the way, let me label this down as the formula for linear expansion. It's the formula for linear expansion. Okay. For volume expansion, we follow the same formula, same pattern. Delta V, change in volume, is equal to beta, that's the coefficient for volume expansion, times the initial volume V sub I times delta T. Okay, so this is for volume expansion. Okay, where B stands for delta V naturally is the change in volume, B is coefficient of volume expansion, and is approximately equal to 3 times the coefficient of linear expansion for the same object. So remember that B is equal to 3 times the alpha. V sub I obviously stands for the initial volume, and still delta T is change in temperature. The only thing to remember here is that for volume expansion, beta is approximately 3a. So there could be problems wherein the beta would not be given, then you'd be asked for the volume expansion, but instead of the coefficient for volume expansion, you're given the coefficient of linear expansion. To solve those problems, you just multiply the coefficient of linear expansion by 3, and then you will get the coefficient for volume expansion. It's very simple, easy peasy, nothing to worry about. Okay, also so this is for solids. We use these two formulas, linear expansion and volume expansion, for solids. But for gases, Well, we use the ideal gas equation. So the ideal gas equation we have over here, we are very much familiar with that one because this one is discussed during your third year chemistry, and also I believe it is also discussed in your third year physics. So we have here the ideal gas equation wherein we have, okay, so we have in the area PV is equal to N R T, where P, okay, P stands for the gas pressure, V stands for the volume of your gas, N stands for the number of moles of your gas, amount of matter or substance contained, R, R stands for the ideal gas constant, what's the value of this constant? Ideal gas constant is about 8.314 joules per Kelvin mole. That's not kilomole, it's Kelvin mole. And T stands for, well, again, the temperature. So, formulas involving the ideal gas equation is just easy. This practically tells us the properties of an ideal gas. Again, let me stress that the units for the following: for pressure, the unit for pressure is the Pascal; for volume, it's the cubic meter, or any unit depending on the constant; moles, obviously mole; and then the ideal gas constant. Temperature is expressed in kelvins or Celsius degrees.